Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 7 on rhombuses. Alright, so we're looking at all now what are known as the special parallelograms, and in our last lesson we looked at rectangles. Today we move on and look at figures that are known as rhombuses or rhombi, if you like it. Alright, so let's talk about these. Another important special parallelogram is the rhombus. The rhombus is often described in earlier grades as a diamond shape. In fact, you may have even had teachers way back, we're talking about like K through 3, show these types of pictures and say, those are diamonds, all right? And, you know, I have no problem with that, but by now, we have to talk about them as rhombuses. So let's look at the definition of a rhombus. A rhombus is any quadrilateral that has four congruent sides, four sides of the same length. All right, now the first thing that we want to do is prove or establish that a rhombus, any rhombus, is also a parallelogram. So let's do that in exercise number 1. Rhombus ABCD is shown below with its congruent sides marked. One set of sufficient conditions for a parallelogram allows us to quickly prove the rhombus is a parallelogram. Which one? Explain. All right, so we had three different ways, three different sufficient condition sets that would prove that a figure is a parallelogram. One of those easily allows us to prove that a rhombus is a parallelogram. Pause the video now and either look back at your notes or in your memory to try to figure out which one it is. All right, well, it's not like I expect you to know these by number, but it was sufficient condition set number 1. So the first thing that we ever saw was that any quadrilateral with two pairs of opposite congruent sides is a parallelogram, right? So that was what we called sufficient condition set number 1, right? Any quadrilateral with two pairs of opposite congruent sides is a parallelogram. Well, that obviously then applies here because AB is congruent to CD and BC is congruent to AD. Now, the fact that they're all congruent to each other is mildly irrelevant for the purposes of what we're talking about right here. Here we've got an opposite pair of sides that are congruent, and here we have an opposite pair of sides that's congruent, and therefore this must be a parallelogram because it's a quadrilateral with two pairs of opposite congruent sides. Simple as that. And again, keep in mind, just like with rectangles, what that means is that now for a rhombus, everything that is true for parallelograms is also true for a rhombus. For example, right? Opposite angles have to be congruent. Adjacent angles have to be supplementary. Diagonals have to bisect each other, right? All of those now must be true about a rhombus because they're true about a parallelogram. Let's keep going on and exploring rhombuses now a little bit more deeply. Properties of rhombuses. Due to having four congruent sides, rhombuses have many additional properties that many other parallelograms do not have, okay? And this is very similar to the fact about rectangles, right? Like for instance, rectangles had congruent diagonals. That's not generally a property of parallelograms, but is a property of rectangles because they have four congruent angles. So let's take a look at the first property of rhombuses. Rhombus property number 1. The diagonals of a rhombus will bisect its vertex angles. All right, so in general, when we draw the diagonals of a parallelogram, if I were to just draw a generic parallelogram, or as best as I can, if I drew in that diagonal, generally speaking, that diagonal doesn't bisect this angle. One of those angles is bigger, one of them is smaller. But I claim that in a rhombus, the diagonals will bisect the vertex angles. So let's try to prove that in exercise number 2. Rhombus ABCD is shown below with congruent sides marked. Diagonal AC has been drawn. We want to understand why AC must bisect angle BCD. All right, and side note, you'll see this a lot in math. We're gonna prove that AC bisects angle BCD. We're not gonna prove that AC also bisects BAD, or if I drew in BD, it would bisect its two angles. Once I've proven that it's true sort of for one of the vertex angles, that same argument would hold true for all of them. All right, so let me just move this up a little bit, and let's take a look at letter A. What special type of triangle is triangle ABC? Justify. All right, well, don't worry about anything else. Just hone in on triangle ABC. What kind of special triangle is it? Pause the video now and write down a name. Well, it's an isosceles triangle, right? It's isosceles because AB and BC are congruent, and any triangle that has two congruent sides is isosceles by definition, right? It's isosceles because it has two congruent sides. All right, great. Awesome, right? Now letter B. Why can you conclude that angle 1 is congruent to angle 2? Right? So I claim that right now you can now conclude that angle 1 and angle 2 must be congruent to each other. Why is that? Pause the video and see if you can write something down. Well, you could write down one of two things. You could either say the base angles of an isosceles triangle are congruent, or you could say that angles opposite congruent sides in a triangle are congruent. I'm going to go with the more common reason, which is that base angles of an isosceles triangle are congruent. And we saw that reason come up quite a bit in Unit 3 when we were doing triangle proof. All right, now let's take a look at letter C. Why can you conclude that angle 1 is congruent to angle 3? So now I'm claiming, let me just look at these little dash lines. Now I'm claiming that angle 1 and angle 3 are congruent. This one's a little bit trickier, but I bet you can figure it out. Pause the video now and see if you can give an argument for why angle 1 and angle 3 are congruent. All right, well, watch the reasoning here, right? So ABCD is a rhombus, right? Which means that ABCD is a parallelogram. Right? That then tells us that AB is parallel to CD, and that then tells us that angle 1 is congruent to angle 3 because they are alternate interior angles. Now think about that. That's a little bit, there's a chain of logic there, right? We know it's a rhombus, and because it's a rhombus, it's a parallelogram. Because it's a parallelogram, opposite sides must be parallel by definition, and then because AB is parallel to CD, angle 1 and angle 3 must be congruent because they're alternate interior angles. And finally, here comes the easy part, letter D. Let me draw all these back in now. Letter D, how do B and C now allow you to conclude that AC bisects angle BCD? Fully justify. Well, see if you can write something down for this. Well, this is cool, right? Angle 1 is congruent to angle 2. Angle 1 is congruent to angle 3. So, right, angle 2 must be congruent to angle 3 by substitution. And that means that AC bisects angle BCD because it divides angle BCD into two congruent angles. How cool is that, right? And it's important, right? The plain fact is the only reason, right, we can say that angle 2 and angle 3 are congruent is because these two sides are congruent, which makes these two base angles of an isosceles triangle congruent. 1 and 3 would have been congruent as long as ABCD was a parallelogram, which it is because it's a rhombus. And then simply by substitution, angle 2 and angle 3 have to be congruent, which means that diagonal just bisected angle BCD. And that is, by the way, true no matter how you slice it with every single rhombus and every diagonal of every rhombus. All right, let's go on and explore more important properties of rhombuses. Let's try that again. Still. All right, now when taken together, the diagonals of a rhombus have a remarkable property that is not true of rectangles, not true of parallelograms. Let's take a look at rhombus property number 2. The diagonals of a rhombus will be perpendicular to each other. Okay, I mean, this is definitely not generally true of parallelograms. It certainly is not generally true of rectangles, right? The diagonals most often do not meet at right angles, but they do in rhombuses. So let's justify that in exercise number 3. In the diagram below, rhombus ABCD has its two diagonals intersect at point E. Letter A. Mark all segments that are congruent based on the fact that the diagonals of any parallelogram bisect each other. State the congruent pairs below. Okay, why don't you go ahead and do that, and then we'll revisit it. Okay, cool. Now we already know that AB is congruent to BC is congruent to CD is congruent to AD, right? But because this thing is a parallelogram, its diagonals bisect each other, so I know that AE is congruent to CE. All right, so I know that AE is congruent to CE, and as well, I know that BE must be congruent to DE. Again, I also know that all of those other segments are also congruent just based on the fact that we've got a rhombus. Now letter B, what triangle congruence theorem could be used to justify that the four triangles below, created by drawing the diagonals, are congruent? Justify. All right, so I can now say that AEB is congruent to BEC is congruent to CED is congruent to AED, right? Why can I say that? What triangle congruence theorem allows me to? Pause the video now and write something down. All right, well, it's side, 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 which is really kind of awesome. You could also, well, no, yeah, you'd have to go with side, side, side. I almost said side, angle, side, but that's not true. You could use side, angle, side to prove that the top and bottom triangles are congruent and the left and the right are congruent. But to actually prove that all four triangles are congruent, you would use side, 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 and it's, it's really simple. It's really just the picture there, right? In each case, we've got AE congruent to CE, we've got BE congruent to DE, and then we've got AB congruent to BC, congruent to CD, congruent to AD, right? Three sides are congruent to three sides, are congruent to three sides, are congruent to three sides. Those are four identical triangles, okay? So now, how can we use that fact to justify that the diagonals are perpendicular to each other? Okay, now think about this for a second. These four right triangles are congruent to each other, right? Those four triangles are congruent to each other. How can we use that now to justify that the two diagonals must be perpendicular? Pause the video now and think about this a bit. All right, well, here it is, right? This angle, and we'll label these in a second, this angle, and this angle, are all corresponding angles, right? They're all corresponding angles in congruent triangles. So angle AEB must be congruent to angle BEC, must be congruent to angle CED, must be congruent to angle AED by CPCTC, right? But these four congruent angles, right? These four congruent angles must have measures that sum to 360 degrees. So each must be 90 degrees or a right angle, right? In all other parallelograms, when you draw on the two diagonals, the four triangles that created are not all congruent. Don't get me wrong, the top two are congruent and the left and right are congruent, but only in the rhombus are four of them all congruent, which makes every one of these four angles congruent to each other. And because all four angles must sum to 360 degrees, each must be a 90-degree angle. And of course, if they're all 90s, even if one of them's 90, that would be enough. But literally, we just proved that they're all 90-degree angles, and therefore the diagonals are perpendicular. All right, now that is one of the most fundamental and important properties of a rhombus, all right? And we will often use both of these properties, what we've learned about rhombuses, to solve a variety of problems in geometry. They'll just kind of pop up, and we'll see them throughout the rest of the course. But let's take a look at one in exercise 4 that's kind of a classic. In rhombus EFGH, EG equals 10 inches and FH equals 24 inches. What is the perimeter of EFGH in inches? Draw a good diagram and show your work. Okay, well, let's take a look at this together, right? So I'm going to draw something that I hope looks like a rhombus, right? Not just like a garden parallelogram, but actually like a rhombus. All right, I'm going to label it EFGH, okay? And we know that EG is 10 inches and FH is 24 inches. And I'll label those eventually, but I kind of want to draw those in. Now, because EFGH is a parallelogram, forget about it being a rhombus, because it's a parallelogram, the diagonals bisect each other. So each one of those is 5, and each one of those is 12. Okay? Now, because it is a rhombus, though, these things are perpendicular to each other, right? We have 4 right triangles that are all kind of identical and arranged sort of like in this circular pattern. Let me take this one particular right triangle out that's got EF right here, right? And it's got 5 and 12. We can use the Pythagorean theorem, right? We can solve for the length of EF, maybe I'll just call it C, right? By doing 5 squared plus 12 squared is equal to C squared. 25 plus 144 is equal to C squared. 169 is equal to C squared. Take the square root of both sides, and C is 13. So in other words, EF is 13. But so is FG, so is HG, and so is HE. So my perimeter is 4 times 13. So my perimeter is 52 inches, right? And think about what's kind of cool about this problem, right? We used 2 things about rhombuses. One of the things we used was the fact that a rhombus is a parallelogram and all parallelograms have diagonals that bisect each other. The other thing we used was the fact that the diagonals of a rhombus were perpendicular, and that allowed us to take any one of these identical congruent right triangles and use the Pythagorean theorem to find the length of its hypotenuse. So watch for the Pythagorean theorem when it comes up in rhombus problems. Okay, let's take a look at one last problem, exercise number 5. In the diagram shown, LMNO is a rhombus. Points P and Q lie on LM and NO such that PQ is perpendicular to LM. It is known that the measure of angle O is 74 degrees. Letter A. Explain why PQ must also be perpendicular to NO. All right, cool. Pause the video now and see if you can think of why or how to justify that PQ is also perpendicular to NO. Well, let's understand the whole PQ is perpendicular to LM. If PQ is perpendicular to LM, then clearly, angle LPQ is a right angle. All right, that's fine, right? But because this is a rhombus, right, it is also a parallelogram. So LM must be parallel to NO. All right, a rhombus is also a parallelogram, so opposite sides are parallel. LM is parallel to NO. Now that means then that angle, right, this tells us that angle PQN is also a right angle, right? That's an alternate interior angle to the one that I drew up here, right, which then tells us that PQ is perpendicular to NO. All right. There's a variety of other ways to do it, but that's a good way to justify it. Now let's take a look at letter B. Determine the measure of angle NRQ. NRQ. In other words, always make sure to first locate the angle you're trying to find the measure of. I want to know the measure of that angle. All right, what I'd like you to do is play around with the properties of rhombuses to see if you can figure out what the measure of that angle is. All right, well, we know that the measure of angle O is 74 degrees. That's 74 degrees, okay? We also know that LMNO is a rhombus, and therefore it's a parallelogram. So I can also say that the measure of angle ONM is 180 degrees minus 74 degrees, or 106 degrees. All right, just be very clear about that. I'm talking about this angle, right? That angle is 106 degrees because adjacent angles in parallelograms are supplementary. But now comes in the rhombus, right? The thing about the diagonals of a rhombus is that they bisect their angles. So I can now say that the measure of angle QNR is equal to 1/2 of 106 degrees, which is 53 degrees. Okay, now just to be very clear, right now, I'm going to blow this up a little bit. I now have the following. And I'm looking for that angle, right? I just took this little right triangle down here and I kind of blew it up there a little bit. I know this is 53 degrees because I know this entire angle is 106 based on the fact that it must be supplementary to the 74, right? The diagonals of a rhombus bisect their vertex angles, so that's got to be a 53-degree angle. And now I can use the fact that the two acute angles of a right triangle must sum to 90 degrees to find my final answer. The measure of angle not NQR, but NRQ must be 90 degrees minus 53 degrees, which is 37 degrees. So there's my final answer, 37 degrees, and I'm sticking with it. Okay, pause the video now and write down any of this work you might need to. All right, let's wrap this up. So today we looked at rhombuses, also known as rhombi, right? We initially proved that every rhombus is a parallelogram and therefore has all the properties of parallelograms. But rhombuses have two additional properties that are exceptionally important, both of which have to do with their diagonals, right? One property is that the diagonals of a rhombus will bisect, cut in half, its vertex angles. The other important property of the diagonals of a rhombus is when the two diagonals are drawn together, they're perpendicular to each other. And that gives rise to all sorts of problems, including things that involve the Pythagorean theorem. Now, we're going to see rhombuses throughout this course, so make sure that you really kind of hammer home on the homework problems tonight so that you'll learn those additional properties that rhombuses have, in addition to all the properties that parallelograms have. I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.